This is a video that relates to Chapter 3 of Preliminary Year 11 HSC Engineering Studies. And we're looking at brakes. What we've just finished yesterday is we finished the mechanics component of Chapter 3. And we'll quickly look, I like to do a look back, so we'll just quickly look back and see what we've learned. So we started with historical developments. We learned about block brakes. We learned about contracting band brakes. We learned about drum brakes in 1902 by Louis Renault. 1902 was also the year that asbestos was first used. We learned about what kind of brakes are these? Drum brakes, excellent. We then learned about disc brakes. Disc brakes have an advantage that because they help heat to dissipate faster, they just improve stopping distances. They're also, I think, less affected by the wet. So we talked about anti-lock braking, only very briefly. We talked about how the advantage is that anti-lock braking has an advantage that allows you to both steer and to brake, which is why the picture for the historical development to braking, I have a picture of the Star Wars game that saved my life, because my anti-lock brakes didn't lock into the gravel. We talked about exhaust and engine brakes. So we talked about Jake brakes, how big trucks, they use air brakes. We talked about how hybrids and electric vehicles use regenerative braking, which means that they, instead of turning the kinetic energy into heat, they turn that kinetic energy into an electrical generator, and they store that energy in a battery, which it's energy for free, because otherwise we'll just go on to heat, and heat's no good for anything. We're not using that heat. Okay, it's also important that we have a hand brake. I don't think I went into a huge amount of detail. So we talked about the effect of people's lives. Really, just generally, we consider better stopping means fewer accidents. Fewer accidents we generally consider to be a societal good, right? We like people not dying generally. Also, the fact is that better brakes allow us to travel at higher speeds. So the speed limits on roads would be a lot lower if we didn't have good quality brakes. So there's a real advantage there. It means that people can get to and from places faster. It means shorter commutes. It also means that our goods that need to travel on roads and rail, that they can be delivered more efficiently, and that means that they're going to be cheaper. So there's some different considerations. Okay, we looked very briefly at the environmental use of materials. And the big thing we considered was asbestos. Asbestos is used, it's been used for a very, very long time. The Romans used asbestos because it's very, very heat resistant. So they would use it for napkins that they would clean by throwing in a fire. The problem is that blue asbestos fibers, what they do is they don't biodegrade, so that if they get into your lungs, there'll be a point that your skin will start to grow over, and then it will continue to grow over and grow over until it becomes a point for cancerous mutations, and that's how you develop lung cancer. So these days, asbestos is banned pretty much everywhere. For a long time, Canada was not allowed to use it, but they were allowed to sell it, and they sold it to places like India. But eventually, India just took the attitude of, yes, even though it's not our place to say that people should value this risk over that risk, it's the generational risk of asbestos, that it's not just current generations. If they were using houses out of asbestos products, future generations would have to worry about it. It's a lot harder to remove. With every generation, it gets harder and harder to remove what's already there. So that's why they ban asbestos. We then learned, okay, so on the mechanics, which we've learned about, the picture for mechanics is what? Yeah, it's a picture of the friction testing machine. So we did an experiment in class where we got a big protractor and an incline plane. Yeah, I used a drawing board, and we made things slide, and we measured the angle, and we took that angle to determine this coefficient of friction. With the coefficient of friction, we then, what do we need to know? Well, we know that the friction force is compared to this normal reaction. Now, I said there's 4 kinds of friction questions. There's boring, bears, boats, and BS. And I said that in year 11, all we do is boring questions. And in boring questions, we can say that the normal reaction is going to be equal to the gravity of the object, mass times gravity, which is better known as weight of the object. So here's an example of a boring question. We have an force is pushing this box. The frictional resistance. We're always looking at a force in equilibrium. So at the exact point where the object just begins to start sliding, and so that's where we're looking where I usually use P for pushing force, or T in the case for boats. We usually have a cable that's pulling the boats, and that cable's under tension. And I say that where P equals F. Here we also have the weight. The weight is going to be a force down. In order to maintain equilibrium, the reaction force, the normal reaction force, will be equal in this specific example. But in year 11, we will worry about more complicated examples, which we've talked about a little bit. This is a good interpretation of that formula. There's lots of different ways we could write it. I like little f is useful. Sometimes I write n with little r. But this that's to help us remind us that this normal reaction is in fact a reaction force. But generally we use the formula FUN, F equals mu n. And that's what you'll see in the formula sheet. We learnt standard coefficient of frictions. I said that brake linings on metal is usually 0.45, but I'll accept a pretty wide range in your calculations if you're making reasonable assumptions. So here we have an example where we have a 200 Newton box is being pushed by we've got to determine the friction. So 200 Newton box, and the coefficient of friction is 0.4. So to do that, what we're going to do is we're going to take 200 times 0.4 equals 80 newtons. Pretty easy, right? One might say boring. This one here, the brake question, is a little bit more complicated. I'm not going to go through this in detail because this is the sort of question that I would use in my brakes engineering report if I had to come up with something. So this would be the sort of example I would be using at the end of that part 3. Part 3.3 would be the friction on the brakes. Okay, we then started learning about stress and strain. We learned about stress earlier. It's the second most important thing you need to know in this course. It's after concrete is made of cement and aggregates. And that is that stress equals force over area. They've written force with a P, which I do not like because you end up getting Spanish pli. But anyway, the next thing we're going to look at is strain. Now, strain confuses a lot of people, but strain is the extension divided by the original length. Now, we say extension, technically it's the change in length, but if we're doing a tensile test, well, tensile means stretching, so it's always going to be extension. Yeah. Now, it's important to remember that strain does not have a unit, right? If we calculate the strain of an object, the strain of an object is unitless. So see here, it's just written as a number. It can be converted to a percentage, but it's just a number. It's a ratio. Okay, stress on the other hand is measured in Pascals. Thank you very much. Excellent answer. Stress and strength are both measured in pascals. So here they have some worked examples which you can go through, but we've looked at a couple already. Now, we have a diagram here that is a stress-strain diagram. When we use a tensile test, which I looked at in previous recordings, when you look at a stress-strain graph, well, when you take a metal sample that you put in a tensometer and you start stretching, you're going to produce a graph. And for mild steel, it will look like this. Mild steel under tensile load looks like this. Except this diagram is what we call the engineering stress, this diagram. There's another version of this diagram. Can anyone remember what that is? There's another version. The true stress, exactly right. Okay, so I'm just going to go to our pictures. Maybe I haven't posted it for you yet. I've only done it for Scandium. There we go. True stress. So we said that engineers are lazy and they get a diagram that looks like this, whereas scientists, and they want to find the truth. And so their diagram looks like this. And the reason for that is because what the blue line is doing is they're measuring by the actual real-time area, whereas engineers, they just measure the area once and that's how it'll be fine. It'll be fine. We'll figure it out. And it doesn't actually change anything, does it? And like, no. But some scientist was looking for a PhD and they're like, I'm going to find the truth. So we don't draw the diagram like this, and it's actually useful for us to have this diagram. This actually helps us. It's better because what it tells us is this is the ultimate tensile strength, this height, this point here. We call that the ultimate tensile strength, and that's way more useful for our calculations. We don't use it very often, but we'll talk later when we talk about punching shear, that we use the UTS to punch through things. And we know that after that point, what's going to happen? What will happen to the metal sample after that point? It'll neck. That is exactly right. It starts to actually pull in, and it starts to shrink at the middle of the sample, right? Called necking. If you go check out the video on tensometers, I'm a little bit hesitant to go and find that now, so we'll just keep going. You know what? Whoa. So that's what necking looks like. And what we get is a terminology is called cup and cone failure. This is the one from the video. I just want to see if we can find cup and cone failure. So they refer to it here. This is the cup fracture and the cone fracture. So that if you have something that is ductile, right, it can be deformed. We'll get, here we go. This is the picture I like to use. So here we can determine that. I wouldn't say it has a great cup and cone failure. It might. It's hard to tell from this picture, but to me it looks like it doesn't much. Whereas this one here, you can see that's the cone, and presumably the cup is on that side. Here we can't tell at all, but we can see the necking. That's from the video. So here we can see this is the cup and this is the cone. And here we have the cone and the cup. They're labeled. Nice. And this one I think is like my classic picture that I like to use. So cup, cone, compared to this one, which is a ductile, which is a brittle fracture. Right, the brittle fracture doesn't have a that cup and cone. So the reason I'm drawing that attention to that is because there's been questions about it. Okay, now for this first zone, if we take a metal ruler, which I'm sure I've mentioned many times by this point, and I start going doing, doing, doing off the side of the table, it usually springs back, but sometimes there's that kid who just pushes just that little bit too far. Right, and they push past that elastic or springy zone into the plastic deformation zone. Yeah, and that bends, and it doesn't. You can't really unbend it. Yeah, you can try to unbend it, but really to take that, get rid of that bend, you need to anneal. Yeah, or normalize or something like that. You have to heat it back up to its recrystallization temperature. So as engineers, we really want to stay in this elastic range, because every time we go over that line, we're going to start introducing serious failure, because it's going to get worse and worse and worse. All of those little failures actually build up. Now, I won't go into too much detail because, one, it's year 11, two, this is me doing a look ahead. We haven't actually covered the chapter properly because we're just looking ahead so you have enough to do your assignment. But so we have this line here that says the proportional limit, and that's the point. We see how this is a linear line, right? It's a straight line. And so we could write an equation about that line. What would we write that? How would we write the equation for that line? We'd say y equals. You guys do maths, right? Sorry? If I said y equals mx plus b is exactly what I'm looking for. What's b in this equation? B is the y-intercept. Where is it crossing the x-axis? Sorry, y-axis at 0. Exactly right. Okay, so what is m? The gradient. Okay, and so how do we calculate the gradient in this case? What would be the rise over the run? Stress over strain will give us the rise over the run. Now, in the case of metals, we talk about that gradient. We give it has a special name. It was discovered by a guy called Euler, but he does kind of get the letter named after him, but we don't refer to it as Euler's modulus. We call it someone else's modulus. Young's modulus of elasticity. And you can remember that Elastigirl, right? If I went to my pictures, it would be the picture of Elastigirl, because she was called that when she was younger. Anyway, and I would play the song by Phoenix. Okay, work, energy, and power. Now, I haven't covered that yet because like I said, this is a look ahead for the sake of the assessment task. But we talked very briefly about hydrostatic pressure, which is why your watch has a pressure rating. Right? If you're a diver, your watch will have a pressure rating. And I said there was one question in 2010 on this, and it doesn't really come up. You absolutely need to know it at uni, but in high school, not so much. Only if you're a mechanical or civil engineer. Probably okay, not if you're telco or not if you're electrical. You might get away without ever learning that, but biomedical probably still needs to learn it. Okay, so what we looked at is Pascal's principle of Pascal's principle, which it says that if you have two enclosed vessels and that they're joined and they're filled with an incompressible fluid, that the pressure on this side will be equal to the pressure on that side. Now, if we say that pressure equals force over area, we can say pressure 2 equals pressure 1. Yeah, and what we've done is I've substituted the letter for pressure, which is because pressure is equal to force over area. So you can rewrite that formula and you can say, well, if I know 2 is going to equal force 1 times area 2 divided by area 1. Now, I don't do it that way. Yeah, you've noticed before that I don't approach it that way. I'm now going to go to the Facebook. Let's go to my albums, and I posted this for you yesterday, even though I'm in a different year group. And this is Pascal's principle, and what we have is I approach these this way. I say, what is the ratio of the two diameters? And then I square them to get the ratio of the two areas, and then I just I multiply the force by that ratio. Yeah, and what I remember is big force equals big area. Now, we also looked yesterday at some questions on how far will this travel, and what we can do is we can remember work. Then remember with machines, this is effectively like a simple machine. We're getting mechanical advantage. We don't get something for nothing, right? If we're getting energy, if we're getting that increase in force, we have to pay that off by a decrease in, we get that increase in force by traveling a greater displacement. And that means that this one, for that same increase, that 16-fold increase, this will travel 16 millimeters for every millimeter that travels. Okay, so that's that same question, but just solved a la Copeland. Solved in the manner of Copeland. Okay, and then this is a picture which could be used in your assignment to describe the forces. There's a force that's applied onto the pedal, the braking pedal. And that gets mechanical advantage through what method? Starts with an L. Leverage. And then that goes to a master cylinder, which the master cylinder then goes to the brake cylinder on each brake. Right? And so because the area is bigger here, we're going to get big force, big area. We're going to get a mechanical advantage by having that big area. And then what we're going to have is we're going to have the calculation of the force, the friction force on the actual brake. Now, yesterday I talked briefly about, here's another example of that network. Here we have a brake. We're going to get leverage. The leverage goes to a master cylinder, which has a small area, and this has a big area. This goes to the brake caliper, and so there's a force. So your assignment should have something that looks a bit like this. Now, I'm not saying this is perfect. I'm just saying this will do. This probably is a sound to a high, not even an outstanding. And like, for instance, do you see how the force is being applied directly onto the brake? It's not at an angle. So it's not as complicated as it could be. So that's probably, that limits it from being an outstanding. So that's the force being applied onto the brake. through, and the leverage is improved. And then here we have the student has then used Pascal's principle to talk about the increase in force. So they said the area is 4 times, the ratio of the area is 4 times. So, sorry, the ratio of the diameter is 4 times. Therefore, the ratio of the area will be 4 squared, or 16. Yeah. And then we have the force that's being applied in the brakes. Again, this is a little bit of a simplified example, but I'm okay with that. Now, I say that just to try and give you some idea of what you need to do to answer this question. Okay, now that we've done that, we've spent 20 minutes looking backwards. We're now going to look again at materials. So the thing is that we generally use steel. Steel is a very, very common engineering product, and especially for cars, steel is incredibly important. Some people consider steel out of date. This is nothing could be further than true, right? Nothing. I'm not going to edit that, but I don't think I said that with the good English. Steel is a incredibly important engineering product. It's also currently the only thing propping up the Australian economy. So steel is typically, it can't have more than 2%. Even 1.5% is pretty high. The vast majority of all steel products, though, have 0.3% or 1/3% of carbon. That's the third most important thing you need to know. And that steel has a yield strength. Let's go back to our diagram. Steel has a yield strength of, a yield strength of 300, this lower yield strength of 300. Now, we talked about the proportional limit. The fact is, we can't really tell where the proportional limit is. We just can't really tell where it is. What we can see, and there's an elastic limit, so the thing is, sometimes it will behave proportionally at a different spot where it stops behaving elastically. So when we talked about how the metal ruler springs, sometimes the behavior they won't be perfectly aligned. But almost always we consider that elastic limit and proportional limit are the same. For our purposes, we can consider that the proportional limit is where the Young's modulus no longer applies. The elastic limit is where it no longer returns to its original shape, yeah, without any permanent deformation. The lower yield point is easy to read. So we use the lowered yield point to be the acceptable amount of stress that we can put on this object as a designer. Now the thing is, in this case, because steel has this bendy bit, it's really easy to read that number on a graph. But some metals, they don't have an easy to read part of the graph. So what we need to do instead is we need to use a, oh, come on, Facebook. Oh, I was going to show my pictures for definite and progressive yield. The definite yield has Dustin Hoffman. Progressive yield has Kitty from Progressive Car Insurance. Anyway, I've talked about this previously, so, you know, I don't need to go into it now. Pop, 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 pop. Okay. Nope, further down, further down. Further down. Okay, steels. Now, we have talked at some fairly extensive length already about how steel is an allotrope, which means it can exist in more than one crystal structure. We have austenite, which exists in what kind of crystal structure? Base-centered cubic. And then we have Alison the ferret. What kind of crystal structure does she have? So ferret has body-centered cubic. Yeah? So austenite, also known as gamma iron, right, is the name given to face-centered structure steel. It only exists at high temperature. Doesn't exist at room temperature. When steel is red hot, it becomes austenite in structure and is often, okay, it can hold more carbon. Ferrite is called alpha iron. It's a body-centered cubic, and it can't hold as much carbon. There's also cementite, which is also called iron carbide, or Fe3C, and it can hold a lot of carbon at room temperature. Perlite is a mixture. It's also the eutectoid. We'll talk about the eutectoid later. But at 0.3%, you get perfect perlite. At 0.83%, what we call the Punset number, we get full perlite. Its structure is called lamella, which just means it has layers. And so there's a layer of ferrite, a layer of perlite. Layer of ferrite, layer of cementite. Layer of perlite. Ferrite, cementite, ferrite, cementite, ferrite, cementite. There we go. It's the word layer was what's messing me up. Okay. If we have less than eutectoid, we use the Greek word for less, which is hypo. Yeah. And we have hypoeutectoid steel, which looks like this. It's made of ferrite and pearlite. If we have more than 0.83% carbon, we use the word for more than, which is hyper, right? And hyper looks like this. I talk about hyperactive kids and kids who have a hypoglycemic. Okay, so here we have the properties of metals as the carbon content goes up. So the big one is the strength goes up until we get to full pearlite, and then it starts going down. Hardness keeps going up with carbon content. Ductility decreases as the carbon content goes up. Okay. Toughness also decreases. Okay. There's something called martensite. How do we produce martensite? Which avatar? What element does the avatar who produces martensite use? Which avatar had PTSD? Quenching, the waterbender. Yeah? So, you take water, you take steel, you heat up to red hot, you quench it in water, and what happens is you get needle-like ore, starts with A. What kind of grains? Starts with A, needle-like or acicular. Acicular. Needle-like or acicular grains. Yeah? So, those grains have a BCT structure, and they are incredibly brittle, and they are pretty hard. They're very hard. They're the hardest. We talked about how Japanese samurai swords, they are an example of something that's quenched but not tempered. But normally what we're going to do is we're going to temper. Do you see the acicular? That would have been a good clue. Yeah, acicular martensite. What does acicular mean? Jack, what does acicular mean? Exactly right. Okay, and what kind of structures does it take, Sarah? BCT is exactly right. Now, look, not everyone needs to know BCT, but okay. Now, after this, I'm going to just refer to, I have another video where I've gone through detail about the different carbon contents of steel. So I have a video that talks about how as you increase the carbon content, I tell people that we know, remember that like rail is 0.6, for example. Whereas razor blades, well, old razor blades, but files, they might be 0.1, 1.2, something like that, sorry, is what I mean to say. We're typically interested in mild steel, right? 0.3, structural work, so structural members are 0.3. And then chains, they have very low carbon. Yeah. So even though steel is anything up to 2%, you can see that, well, we really don't go to 1.5 is incredibly high carbon. Okay. Now, then I have a whole nother video which we're going to look at later, which talks about different additives. You can add magnesium, sulfur, chromium, nickel, molybdenum, vanadium, tungsten, copper, silicon, boron. And then we talk about cast irons, stainless steels. They're covered in chapter 4, but I'll do them in the same video. And then we have cast irons, and they also have additives, right? We use silicon to produce more graphite, and we're going to learn about a whole bunch of different kinds of silicons, and I use my Dragon Ball Z reference about transformations. And then we're going to now focus on composite materials. We've already talked a lot about how wood is a composite material, right? All timber by definition is a composite material. Wood is what I call dead trees. Timber is when you cut them up into rectangles, and you usually, you dry them out, and you get them ready to be used. So that's what wood is. But by definition, it's always, so volume 2, chapter 1 means year 12, the start of year 12. We go into this a little bit more detail. We learn about engineered timbers that are used in constructions, because these days you can't really buy, 6 meters of oak anymore. It's just too expensive. So instead people use manufactured, where we take timber, we machine it, and we put it together, we improve its strength. But all timber, by definition, is a composite because it's cellulose fibers in a lignin resin. We've talked already about asbestos a little bit above. You will research asbestos as part of your assignment. Now, the thing I want to talk to you about today is, because I have it in my hands, is I have a sintered metal. I have two pieces of sintered metal. I have two parts that have been made through what we call powder metallurgy. And what powder metallurgy is, well, you take some metal and you put it as a powder and then you press it under heat until it forms its shape. And they feel pretty strong. But the thing is, if you got a couple of spanners or you put them in a vise and hit it with a hammer, they would shatter because they're not very strong. They're strong enough that we can use them for things. And I always like to say Happy Meal toys. Imagine a Happy Meal toy. No one wants to grind out the gear that goes into a Happy Meal toy. Yeah? So for a Happy Meal toy, for things like, so we have like, that's a fitting for a pneumatic connection, right? Those sorts of things, they need to be incredibly accurate, right? No one wants to machine that, but it doesn't need to be very strong. So if we need things that need to be dimensionally accurate but not very strong, powder metallurgy is a great option. There's some other places where it's good. If you need something that's self-lubricating, if you need to use things that can't be machined, like tungsten carbides can't be machined, if you need to use metals that won't alloy. So if you have, say, like copper and tungsten, they won't alloy together. So you might have something that needs good conductivity but needs to be wear resistant. You'd use powder metallurgy for that as well. Okay. Again, not in the assessment task, but I'm going to talk about that now. Now, here we have some different stress-strain graphs, and we can use these stress-strain graphs to determine the properties of the material. If it's tall, that means it's strong. If it's wide, that means it's ductile. Now, some things are strong and ductile, like steel. Steel is strong and ductile. And because it's got a big area under the curve, it would use a lot of crayon to color in underneath that curve. We can call that tough. The area under the curve is a measurement of toughness. Now, if it curves like this, that means it has plasticity. That means it can be deformed and made into a shape. So cars, they're made into shapes of things, right? Whereas if they're straight like this, it means that they're brittle. It means that they snap very quickly. So glass, well, glass wouldn't be that tall, but some metals, for instance, I don't want to overcommit here, but so carbon fiber has good strength, but it doesn't have a lot of ductility, so it will shatter. Okay, so we'll go through this again in greater detail later. Now, when we revisit this, we're going to look at videos of, it's in the same testing folder on Facebook, that same picture of Sam Rockwell. It has a concrete compression test. So when we test concrete, it's important that when we build a building out of concrete that we know that we're using concrete that's strong enough, right? The problem is you don't want to have a concreter or even worse, the guy in the concrete truck. If he wants to go and visit his mate, and he gets caught up in traffic, and he's got the concrete in the back, and it's all going hard, well, what he might do is he might pour some water in there to slow down the setting of the concrete, not realizing that it's going to drastically decrease the strength of the concrete. Well, he probably knows that, but the point is, if you throw things into the back of the concrete, it might damage the quality of might decrease the quality of the concrete. So on site, a junior engineer, their job is to make concrete cylinders that they'll test in a lab to make sure that we haven't been ripped off. Right? I've done this job as a junior engineer. So we put them in a testing machine, which I'll show you a video in a second. We have 4 hardness tests. So we have 4 hardness tests. This is why the picture for the materials video is a picture of Vicus. It's actually spelt differently, but Vicus from District 9. Because in District 9, he tries to give people cat food. And I try to remember that the Vicus test is good for the cat food tins. If you got thin metals, you want to use the Vicus test because it's only very thin. The cat food tin, it's not a thick metal. It needs to be thin metal. You use the Vicus test for the thin metals. The Brunel test uses a ball instead of a diamond-shaped thing. It doesn't use the pyramid shape. It uses a ball shape, and it leaves a big, bad ball bruise on the steel, which damages it, right? It's bad. So I remember Brunel is from the before time. It's bad because it uses a ball, right? We don't really use Brunel very much. We can, but it's a destructive test, right? You can't use it on the sample you actually want to use. Whereas the other 3, you can use them on something and then still sell it to the person. Here we have a Rockwell hardness tester. I think it's broken, but we have one, and I like to point it as like a prop. right? And that's why there's a picture of Sam Rockwell on that post, the Facebook post. And then we have the Shore Scleroscope, which is portable. I will show you a video about chocolate that's harder than steel, right? And that's because steel has a big range of hardness depending on how much carbon content it has, right? Because I had students say, yeah, but if it's harder than steel, then how are they cutting it, sir? I'm like, well, they're using tool steel to cut it, whereas it's harder than low carbon steel. Okay. So this is a tensometer. No one uses these tensometers anymore because they're just not accurate enough. But school teachers would have used them 20, 30 years ago. Now these days, tensile tests, those machines cost tens of thousands of dollars. The Rockwell hardness test, I haven't fixed our one because it would cost, again, thousands of dollars to repair. And these days, a modern one would cost $10,000. Okay, and then we're on to communication. That's our look ahead at materials. Now, I know that when in that video, it looks like I've said, hey, a lot of these things we're going to cover. You know what? We've got a little bit of time. Let's start looking at them now. So we're going to go, just hold on while I go through. Testing. So, 1, 2, 3. In this picture, I have every single bit of testing that we do in engineering, in HSC engineering. So it has year 11 and year 12. Which some people like, some people don't like. I like having it all in one spot. So what we have is tensile tests, which I've already referred to in this video. We stretch out the piece of metal and we'll eventually get the necking. There we go. And then it will snap and we'll get a cup and cone failure. And then we have compressive tests. These ones are pretty important. Okay, so what we do, I'll give this a bit of sound. Pretty exciting. Yep. So what we do is we take a concrete cylinder. How do we get the concrete into a cylinder? Well, let's see if this picture will work. Always a bit of a risk, this one. Okay, so how do we get these concrete cylinders? Well, what we do is we pour the concrete into a mold, and the mold can be released, kind of like a cake tin. You can take the screws off. You lubricate it as well first so it doesn't stick to the metal. And then you store it. I might have down here curing. Okay, so then you store it in water because the water makes it stronger, right? If you if you keep it wet, concrete will keep getting stronger forever. But there's actually always a little bit of increased strength. But generally, what we're interested in is see how most of the strength comes around this 28-day mark. Yeah, most of the strength comes around at 28 days. So we usually test on 28 days. But just to check that things aren't like going to hell, we also test on 3 days and at 7 days. And if they're not following where the curve should be, we call up the lab would call up the engineer and say, you have a problem. You might want to consider investing in a jackhammer, because they will start jackhammering out the concrete while it's still getting stronger. Because if that concrete's coming under strength, if you ordered 40 MPa concrete, right, 40 megapascals, and instead you only got 10, if the lab, they know what it's going to come out at. They'll look at a 3-day report and they'll say, I don't think this is going to cook. This souffle is not going to rise. Grab the jackhammer and get some boys and get them taking that concrete out, because otherwise you just have an absolute disaster. It's an expense. People will be going to court, and they will be arguing who is at fault, but they will jackhammer that concrete out and put in stuff that's the right strength. So that's why we do these tests. And so at 28 days, that's when it needs to, that's where the court will say whether or not you have met your contract obligations. They'll base it on their 28-day test. But if we leave it just in air, the same sample will only have 30 megapascals. If you give it 7 days in water, you'll get 35 megapascals. Whereas if you put it in water for the whole time, you'll get like 42 megapascals. And it'll actually keep going up if you cure it. But the thing is, you can't have like a construction site covered in water, right? So what do you do instead? Well, what they do instead is they get Hessian, right? They get like fabric and they put it out, or they can put sand and they get sprinklers and they'll water it down for at least a week. There you go, my mate Sam. So here's some questions I found recently. So this is like a, you know, we can see sort of this cup failure here. Sorry, cone failure there. Okay, so that's the concrete compressive test. There's, in year 12 we'll learn about slump tests. Slump tests are a way that you can just tell whether or not the concrete's too sloppy or too dry. And that's an important thing. So before you get the concreters, before you have that disaster where you need to get the guys with the jackhammers, what you'll do is you'll actually do this test on site, and you'll measure how much it slips, or slumps is probably the better term, and you measure how far it is from where it starts. And if it's too low, if it's too high, it's a good problem. You can just add water. You call up the lab, or you call up the provider and say, hey, the concrete is coming in, I'd say 5 inches or 120 mil. That's too wet, right? And so if it's too wet, you call up the lab. If it's too dry, well, not the lab, you call up the concrete company, and you say it's coming in too wet, or you say it's coming in too dry, and they will tell you, okay, you're allowed to do X. They'll say, put in an extra cup of cement, or they'll say, yeah, add an extra 2 liters of water. And they'll make that call as to what you're supposed to do. Anyway, we don't learn that until year 12, so a little bit ahead. There's these other tests we talk about, transverse tests. This is how engineers were able to design concrete beams, by doing these real-world tests where we made concrete beams and we observed how they break. And so you can see how the failure usually starts happening here. And it gives people plenty of warning. It means if you're living in a house and you start to see this massive crack, you go and say, hey, there's a problem, so that you know the house doesn't fall on your head. If you design the reinforcing in the wrong way, if it's what's called over-reinforced, it might fail without warning, and that's really dangerous. Okay, we have X-ray and gamma ray tests. I mean, that's pretty much what it sounds like. Dye penetration tests, they're exciting. We'll learn about them next time. Sorry, in year 11, in year 12. I'll just show you that they look pretty cool. That they make this, you spray it, and then the cracks, they just show up out of nowhere. These microscopic cracks suddenly become visible. It's pretty amazing. Okay. I'm just showing you that one because that one I think is actually like a lot of fun. Okay, so we have hardness tests, and so hardness tests look like this. So like I said, our machine there would cost thousands of dollars to fix. You can only imagine what this machine costs, right? So a Rockwell hardness test is conical. The sample is conical. And it goes in the machine. And then, if you look at the Brunel test, literally the same guy, right? Literally the same guy, same machine, but what he does is he uses a sample that is a ball. Remember we said that they're bad because the big ball bruises, and that's bad. You can't sell it anymore. It's they consider that to be a defect. And so now this is a Shore test, and Shore, you just use this little thing here, and you can actually just hold it in your hand. And the advantage of that is this one's portable, right? So this one, the Shore scleroscope is portable. There's also a durometer as well, which is the smaller one. They can be compared. There's conversion tables, and in the other video I actually had conversion tables. I don't talk about Vickers here. I guess the reason I don't talk about... Was anyone remember where do we use Vickers? I said earlier. For the thin metals, for the cat food tin. So the reason for that is I show this video of District 9. This guy here, his name is Vickers. It's set in South Africa. That's why I'm trying to do the South African accent. And he tries to give people the cat food. We'll say to distract them. He starts, start throwing cat food. Throw the cat food. And it's like, is that tear gas? It's like, no, it's cat food. Anyway, and later to get someone to sign a contract so that he'll give up his home, he offers him cat food so that he'll sign the contract. Anyway, so cup and cone fracture, I talked about that. Now, hardness, it's interesting. Why razor blades dull when my beard hair is not harder than the razor blade steel? So why do they dull? That's a complicated question, which someone at MIT probably got a PhD from. Daddy Pig is a famous concrete expert. He's like, oh, I'm sorry, I did not realize I was dealing...
Mr. Pig, you must be coming to test our concrete. Yes. Do you know me? Oh, your work in concrete is famous in our country. Oh, but I have disturbed you. Good night.
And then later, Daddy Pig asks for orange juice and coffee, and Mrs. Rabbit's like, no, I don't think we can do that.
No, coffee or orange juice. You can't have both.
I don't think we have to be so strict with the famous Mr. Pig. Coffee and orange juice.
Thank you. Excuse me, I am King Alfonso. Could I have a coffee and orange juice too?
No, that is impossible.
So, the point is, if you go into materials testing, you too could be as famous as the famous Mr. Pig. Okay, I have a video here on ultrasonic testing, eddy current testing. This doesn't relate to you. Casting concrete cylinders. This is just if you want to learn more about how you cast concrete cylinders. Technically, that process that we talked about here with the... that process of wetting down the concrete is called curing. You can cure lots of things. You can cure like tobacco, for example. I'm sure there's hundreds of other things you can cure. You can cure meat, right? The process of curing concrete is by making sure, because it's a chemical process and it produces a lot of heat, which means that the water leaves when you actually need that water to continue the process. So you need to keep providing additional water so it doesn't evaporate out. And that's called curing. So this is a song by The Cure, but it's played in the form of a mariachi band because everything sounds better in the form of mariachi form. Okay, if you're ever having a party, you don't know what to put on, mariachi music. Everyone loves mariachi music. It's a crowd pleaser. And I think on that important life lesson, I'm going to call it and say, yeah, that's materials testing. Have a great weekend, everybody.